Welcome to the 18th lecture of the MOOC on parallel algorithms. In this lecture, we are going to revisit a problem we have seen before, namely sorting. We have seen a couple of algorithms for sorting before. In particular, we consider algorithms on comparator networks. We saw that algorithms that we design for comparator networks can be simulated on ER-EWP RAMs for the same time complexity and processor complexity. We designed two algorithms that runs in order of log squared in time using n processors. That is, the complexity of the algorithm was order of n log squared n. These algorithms are due to Batcher. So, they were the odd even merge sort and the bitonic sort merge sort. But then we know that the sequential time complexity of sorting is order of n log n, theta of n log n to be precise. So, the algorithms that we discussed there were not optimal. They had a cost of order of n log squared n. So, they were not optimal. They were divide and conquer algorithms. And essentially they use a merge network as the basic building block. So, they are merge sorts. Now, in the last lecture we saw an algorithm for merging two arrays of size n each using n by double log n processors in order of double log n time. This is an optimal merge algorithm for the CR-EWP RAM. Now, once you have an optimal merge algorithm, you can use it to construct a merge sort. So, let us see how we can use the merge algorithm that we saw in the last class to construct a new merge sort. So, let us say we are given two sorted arrays of size n each. And we have, let us say, n by double log n processors. So, what we do is the classic divide and conquer, divide the array into two segments. Sort each segment recursively with half the processors, and then merge them using the algorithm of the last class. So, that is what the algorithm is. So, to merge, we would require merging of an array of half the size plus double log n time. So, this is what the time complexity is. So, if you continue like this, which if you continue will come to, after k levels of unrolling, we will have so, if you put k equal to log n, you find that this is order of log n double log n. So, with n by double log n processors, we managed to sort in order of log n double log n time. Therefore, this algorithm is optimal and is an improvement over batches algorithms for the CR-EWP RAM, because batches algorithms run in order of log squared n time, whereas here this algorithm runs in order of log n double log n time. So, using the algorithm of the previous class, we can immediately obtain a sorting algorithm which is faster than batches sorting algorithm. But the algorithm that we are going to study today hereafter actually does better. This is the algorithm that is famous as Cole's merge sort, after its inventor Richard Cole. So, in Cole's merge sort, we managed to sort n elements in order of log n time using n processors. We shall study the version of the algorithm that runs on a CR-EWP RAM. In fact, you can improve the model to ER-EWP RAM for the same time and processor complexity, but this version we will not study in this course, because the algorithm is slightly more complex when we come to the ER-EWP RAM. So, we will study the CR-EWP RAM version of Cole's merge sort. Now, Cole's merge sort is a pipelined algorithm. A pipelined algorithm is where you divide the algorithm into several components and the data flows through the components in this fashion. So, all the data is not sent through the algorithm simultaneously. A part of the data is first given to block 1. After block 1 has processed the first part of the data, it sends it to the second component. So, when the second component is processing the first part of the data, the first component will take the second component of the data and process it. After that, all the data will be sent one step forward. The first part of the data, when it reaches the third component, the second part of the data would have reached the second component, and the third part of the data would have reached the first component of the algorithm. So, the data pulses through the components of the algorithm in this fashion. Therefore, we get a speed up. Such an algorithm is called a pipelined algorithm. This is very similar to the pipelined architecture you would have studied in advanced architecture courses. The same idea is being employed here. So, in Cole's merge sort, let us say we are given an array of n elements to sort. Let me assume that n is an exact power of 2. Otherwise, we pad the array with dummy elements that are larger than all the given elements. So, those dummy elements after sorting will be at the right end and can be removed. So, let me assume that n is an exact power of 2, and then what we do is this: we construct a binary tree on top of this array. So, this is a binary tree with n leaves. So, it will have log n levels above the leaves. So, let us say the leaves are labeled 0, that is the leaves are at the 0th level, the parents of the leaves are at level 1, then we have level 2 and so on, and the highest level is labeled log n. This is where the root is. So, we construct a binary tree on top of the given array of n elements. So, this binary tree has log n plus 1 levels on the whole, the leaves are at level 0 and the root is at level log n. And then in this binary tree, we add some extra data structures. At each node of the binary tree, we have two arrays. One array is called a cache and the other array is called a sample. Both of these have a size of 2 power L, where L is the level number. Which means leaves have caches and samples of size 1 each and the root has cache and sample of size n each. The roots have the cache size equal to the sample size equal to 1. The leaves. The leaves have cache and sample size of 1 each. Parents of leaves have a size of 2 each. In general, nodes of level k, nodes of level L have a size of 2 power L. The root has arrays of size n each, because the root is at level log n. So, after setting up arrays in this fashion, except for the leaves, the arrays are initially empty. The caches and samples of all nodes other than the leaves are initially empty. For the leaves, the input nodes occupy the caches. Remember, the leaves have caches of size 1 each. So, the cache can hold only one element, one input element is held by each node. The sample arrays are empty for the leaves as well. So, at the beginning of the algorithm, the sample arrays are empty all over. The cache arrays are empty everywhere except at the leaves. At the leaves, each cache will hold one element. The cache is of size 1 and it holds only one element. And then our algorithm executes in a number of stages. The algorithm is made up of several stages. As we shall see, there will be 3 log n stages. In the algorithm, there will be 3 log n stages when we have n items to sort. We shall end up showing that each stage executes in order one time. Therefore, the overall running time of the algorithm will be order log n. So, a stage will execute in order one time with n processors. So, with n processors, the algorithm will run in order of log n time. So, let the stages be numbered from 1 to 3 log n, and the algorithm proceeds in this fashion. let me specify a stage for a node u at level k, let us say, with v and w as its children. So, let me specify in particular the teeth stage. So, I am going to specify the teeth stage for a node u at level k with v and w as its children. So, in the stage we have two steps. In the first step, we draw samples from the cache of u to form the sample of u. In step 2, we merge the samples of the children, in this case v and w, to form the new cache of u. So, a stage of the algorithm consists of these two steps. In the first stage, we draw samples from the cache of u to form the new sample of u, and then we, in step 2, we merge the samples of the children v and w to form the new cache of u. So, here some definitions are necessary. So, let me define Ct of u as the cache at u after the teeth stage. Similarly, by St of u, I will denote the sample at u after the teeth stage. Likewise. Now, with these, let me give more specification for the steps of a stage. In stage T, a node u at level k with v and w as its children does this in step 1. It draws samples from the old cache at u to form the new sample at u. So, this is how St of u is formed. Once it is formed in step 1, it does not change in this stage. So, in stage T, St of u will be formed by drawing samples from Ct minus 1 of u. So, the drawing of the samples is done like this. If the stage number T belongs to this range, that is 2k plus 1 to 3k plus 1. Remember, k is the level number of node u for which we are writing the stage. So, if the stage number T belongs to 2k plus 1 to 3k plus 1, this range, then we pick every fourth item from the right hand side as a sample. The sampling is done like this. If T belongs to the range 2k plus 1 to 3k plus 1, then we pick every fourth item from the right hand side as a sample. Else, if T is 3k plus 2, we pick every second item from the right hand side as a sample, and finally if t equal to 3k plus 3, we pick every item as a sample. So, once again the samples are picked from Ct minus 1 of u, which is the cache at u at the end of stage t minus 1, in this fashion to form the sample array of u that must be left behind at the end of stage t. So, the sample array is formed in this fashion. If the stage number t happens to be between the range 2k plus 1 to 3k plus 1, is within this range, where k is the level number of node u, then we pick every fourth item from the right hand side of Ct minus 1 of u as a sample. Else, if t is 3k plus 2, we pick every second item from the right hand side of Ct minus 1 of u as a sample. Else, if t equal to 3k plus 3, we pick every item as a sample, that is every item of Ct minus 1 of u. So, these are the actions for step 1. Remember, if t happens to be greater than 3k plus 3 or less than 2k plus 1, there is no sampling. The sampling will happen at u precisely when t is within this range, that is t is within the close range of 2k plus 1 to 3k plus 3. Outside of this range, there will be no sampling at u. So, whether sampling will happen at u depends on both t and k, where t is the stage number and k is the level number of u. Then, after having formed the samples, in the second step of the t stage, what we do is this: we merge the samples that have just formed at the children st of v and st of w to form Ct of u. So, at the end of the stage number t, Ct of u is the cache at u. This will overwrite Ct minus 1 of u, from which we had been picking the samples. So, what happens is that node u, which had cache Ct minus 1 of u, will generate the sample st of u. At the same time, the children v and w of u will also be doing the same thing. From Ct minus 1 of v, we would be forming the sample st of w here. From Ct minus 1 of w, we will form st of w, and here from Ct minus 1 of v, we will form st of v. And then the samples st of v and st of w will be merged to replace Ct of u. The result of the merge of st of v and st of w will be replacing the cache at u, and this replaced cache will form Ct of u, the cache at u at the end of the t stage. Simultaneously, the caches at v and caches at w will be replaced by the samples of their children merged appropriately. So, all the caches at all the nodes will get updated simultaneously. So, that is the structure of the algorithm. Now, let us take an example and see how the algorithm works on real data. So, let us say we have the key values from 0 to 9 followed by a to z. Let us say this is the increasing order, 0 less than, 1 less than, 2 less than, etc. 9 is the largest, then 9 is smaller than a is smaller than b, and so on. So, we shall assume this linear order for the key values. So, with these key values, let us say we have an input that we want to sort. We will take an input of size 32. So, let me consider one half of the input. those are the first 16 elements. Then the next 16 elements I will draw in the next screen. So, let us say these are the 32 elements. These elements occupy the cache arrays of the leaves. So, what I have drawn now are the leaves, the caches of the leaves. So, the caches, the cache arrays of the leaves are full when the algorithm begins. So, we assume that at the end of the hypothetical stage 0, all the cache arrays of the leaves which are at level 0 are filled. Then in stage 1, the leaf nodes are supposed to pick every fourth element from the right hand side as a sample. But then since the cache arrays at the leaves have only one element each, you will not be able to pick any element here. So, in the first stage actually nothing gets done. Every leaf is attempting to pick the fourth element from the right hand side of its cache array, but since the cache array has only one element, nothing gets picked. So, no sample is picked. So, the first step is essentially a dummy step. We will keep numbering the steps in this fashion so that the induction holds good. So, for the purpose of the induction, we assume that in the first step nothing happens. In the second step, every leaf node will attempt to pick the second element from the right hand side as a sample, but then again since the cache has only one element, nothing gets picked. So, the second step is also a dummy element. Now, in the third step, every leaf node will pick all the elements in its cache array into the sample array, which means the elements are copied into the sample arrays of the leaves. So, the sample arrays will look exactly like these, and then in the second step of stage 3, the sample arrays of the children will be merged into the cache arrays at the parents. So, now the parents of the leaves are going to get something in their caches. So, the parent of the leftmost nodes V and L will get these elements in sorted order in their cache arrays. So, the parent will end up getting L and V in sorted order in its cache, and these two nodes will get 9 and E, which is the sorted order, and here it is 4 and K, and here it is 8 and T. They are already in sorted order. M, W, C2 are not in sorted order, so they will be put right 2C. J, S are in sorted order, and then 7D. So, this is what happens at the end of the third stage. For the second half of the tree, we will have UI, BR, 3N, 5G, PQ, AF, 6X, and HZ. So, the cache arrays of the parents of the leaves are filled at the end of the third step. So, we are now at the end of the third step. Then in the fourth step, the leaf nodes are done. So, there will be no more drawing of samples from the leaf nodes, but the parents of the leaf nodes will attempt to draw every fourth element from the right hand side of their cache arrays as samples. But then these nodes have only two elements each, so nothing gets picked. Therefore, the fourth step is also a dummy step like the first and the second steps, but we will keep it in so that the induction holds good. Now, in the fifth step, these nodes, that is the parents of the leaves, will attempt to pick every second element from the right hand side as a sample. So, in particular, the node which contains LV will pick L as a sample, and the node which contains 9E will pick 9 as a sample. And then in the second step of the algorithm, 9 and L will be merged at the parent. At the end of the fifth step, we are at the fifth step now. At the end of the fifth step, the cache of this node will contain 9 and L. That is because L is chosen as the sample of the left child and 9 is chosen as the sample of the right child. So, the parent will end up getting 9L. Here we have 4 and 8 coming in, and here we have 2 and M, and here we have 7 and J. In the second half of the tree we have U and B, and here we have 3 and 5, and here we have A and P, and here it is 6 and H. So, at the end of the fifth stage, this is how the cache arrays will look. So, by the end of the third stage, the leaf nodes were done, they are not drawing samples anymore. So, now we are done with the fifth stage. Now, in the sixth stage, nodes at level 2, the leaves are at level 0, these are at level 1 and these are at level 2. The nodes at level 2 will attempt to pick every fourth element as a sample, but then since they have only 2 elements each, nothing will be picked as a sample. But then their children, that is the nodes which are at level 1, will pick every element as a sample. So, L and V will come as the samples from the leftmost node, and 9 and E will come as the samples from the next node. Now, in the second step of the stage, these will be merged at the parent. So, the parent at level 2 is now going to contain 9ELV, and here we are going to get 48KT, then 2CMW here and 7DJS here. At this point, all these level 1 nodes are done. So, this is in the left half of the tree. In the right half of the tree, we have BRUY, (35GN), AFPQ, 6HXZ. So, at the end of the sixth step, all these nodes are done. So, that is the tree as it looks like at the end of the sixth stage. Now, we come to the seventh stage. In the seventh stage, levels 0 and 1 are done, but level 2 can still emit samples. So, here level 2 will pick every fourth element from the right hand side as a sample. So, from this node we will get 9, and from the next node we are getting 4. So, these will merge to form the cache at the parent. So, at the parent now we have 4 and 9 forming the cache, and here we have 2 and 7 forming the cache. That is because 2 is picked as the sample from this node and 7 is picked as a sample from this node. In the right half of the tree, we will have 3 and 5 coming here, 3 and B coming here, and here we have 6 and A coming from the children. So, this is what happens at the end of the seventh stage. So, at the end of the seventh stage, levels 2 and 3 are still active. Level 2 is emitting samples and level 3 hasn't started drawing samples yet. And then in stage number 8, the level 2 nodes will be picking every second element from the right hand side as samples. So, the node which contains 9ELV will pick 9 and L as samples, and the node which contains 4, 8 kt will pick 4 and k as samples. So, in the second step these will be merged at the parent. Now, at the parent, since this node, that is the level 3 node, is picking every fourth element from the right hand side as a sample, nothing will be picked. So, the fourth level will not be populated yet. So, in the 8th step we have 4k and 9l coming up, that will be 49kl. Here we have sorry, it should have been 2 and 7 here. Now, we have 2m7j coming up. So, we have 27jm here, and here we have bu and 3g coming up. So, that will be 3b gu, and here we have ap and 6x coming up. 6a p x would be the sorted order. So, this is how the tree looks like at the end of the 8th stage. Now, when we come to the 9th stage, the level 3 nodes will pick every fourth element as a sample and send upwards. So, now the fourth level will be populated for the first time. It will be getting 2 and 4 at the fourth level in the first half of the tree. In the second half of the tree, we will have 3 and 6 coming to the fourth level. That is for the fourth level. Now, for the third level, we get samples from the second level, but the second level is now picking every element into the sample array. So, the sample array of the node which contains 9ELV in the cache will be the same, that is 9ELV. All the elements are now moving upwards to the third level. Similarly, 4k, 48 kt will be sending all those elements upwards. So, at level 3 now, we will have all the elements in sorted order. That is, we will have 4, 8, 9e, kl, tv. And here at the next node, we will have all the elements in sorted order, which is 27 CD JM SW. That is in the first half of the tree. In the second half of the tree, we have three, 5 BG NRUI. These are the elements coming from the two children. AFPQ and 6HXZ merged will form the cache which will replace 6APX. So, 6APX will be replaced with 6AFHPQXZ. With this, the second level is also done. So, by the end of the 9th stage, you can see that the third level is full. That is, the third level has acquired all the elements in the leaves of the subtree that is rooted there, which means the subtree that is rooted at this node contained 6AFHPQXZ. This is the sorted order of the actual set. The actual set is listed at the leaves in the order PQFA 6XZH. This gets sorted into 6AFHPQXZ at this node. Similarly, at every level 3 node, we have now collected all the leaf contents of the subtree rooted at that node in sorted order. So, level 3 nodes are now full. They are not done with sampling yet. Level 2 nodes are done with sampling, but level 3 nodes have just become full in their caches, but they have still more sampling to go. So, now we come to the 10th stage. In the 10th stage, we will be picking every second element from these nodes, the level 3 nodes, as samples. So, we will have 4, 9, k and t as the samples from here and 2C JS as the samples from here. Level 4 nodes will attempt to pick every fourth element from the right end, but since they have only 2 elements each, they will not be able to pick anything. Therefore, there will be no data moving from the fourth level to the fifth level yet, but the caches will now be replaced with the sorted order of these elements 2, 4, 7, 8, 9, C, D, E, J, K, L, M, S, T, V, W. So this node has collected these, we will be picking only the marked elements. This will happen later. At this point, we will be sorting 49KT with 2CJS. So we have 24, 9C, JK. So at the end of the ninth phase, that is what we have. The nodes at level 3 have become full. Now we come to the 10th stage. In the 10th stage, we will be picking every second element from the third level 3 nodes as samples, and they will be transported upwards. At the level 4 nodes, since we have only 2 elements each, nothing will be picked as a sample, so nothing will be sent to the fifth level yet. From the level 3 node, here we will be picking 49KT and 2CJS respectively to send upwards. So we will have 249C JKST at this node, and here we have 3BNU going up and 6FPX going up. So we will have 36BF NP UX at this node. So at the end of the 10th stage, this is what the array looks like. And then in the 11th stage, the level 4 nodes will be picking every fourth element, which means it will pick 3 and N to send up, and this node will pick 2 and J to send up. So we will have 2J, 3 and N going up. So at the fifth level, we will have the sorted order of those elements. That is what happens in the 11th stage at level 4 nodes. At level 3 nodes, we will be picking every element from 3, and then all of them will be sent up. Sorry, we are at the 12th step. In the 12th stage, we will be sending every element from the level 3 nodes upwards. So level 4 node will now end up containing every single element. So level 4 node becomes full at the 12th stage. So that is how the algorithm proceeds. So I am leaving the rest of the tree for you to sketch up. So you can see that at the beginning of the algorithm, which I can assume is the end of the hypothetical 0th stage, for the sake of the induction, I will assume that we are at the end of the hypothetical 0th stage. We assume that we are at the end of the hypothetical 0th stage. At this point, we find that the leaves are full. So this forms the basis. So inductively, I want to argue that level k nodes become full at the end of the 3kth stage. This is what we want to claim inductively, for which the fact that at the beginning we had the leaves full will form the basis. We assume that the leaves are at level 0, and at the end of the 0th stage, which is a hypothetical stage, the leaves are all full. So that forms the basis. Now, by inductive hypothesis, we have that level k minus 1 nodes become full at the end of the 3k minus third stage. Then from the algorithm we see that in stage number 3k minus 2, level k minus 1 nodes picks every fourth element as a sample. In stage number 3k minus 1, level k minus 1 nodes pick every second element as a sample. And in stage 3k, level k minus 1 nodes will pick every element as a sample. But mind you, this is out of the caches that have already become full, which means all the nodes, all the elements that were placed at the leaves of a subtree of a level k minus 1 node has now actually reached the level k minus 1 node. Therefore, in stage 3k, when we pick all of them into the sample array, the sample arrays will become full. Now, in the second step of stage 3k, all these elements will be merged into the caches of their respective parents, and these parents are at level k. So, what we find is that in stage 3k, level k nodes get all the inputs in their subtrees in their caches. In other words, these nodes are full. That establishes the induction. So, what we have shown is that at the end of the 3kth stage, every node at level k has got its cache full. So, in particular, the root, which is at level log n, becomes full in stage number 3 log n, which means if we run the algorithm for 3 log n stages, at the end of this stage, the cache of the root will become full. In other words, the cache of the root will contain all the input elements in sorted order. So, at this point, all we have to do is to output the cache of the root, which means sorting will be accomplished in 3 log n stages. Now, what we have to establish is that each stage can be executed in order 1 time. But how do we achieve order 1 stages? To achieve order 1 stages, we have to do what is called merging with covers. we say that an array is a cover of another one. In particular, we say that an array C is a decover of array B if between any two elements of C there are at most D elements in A. So what we are going to show is that if two sorted arrays A and B have a cover C, that is, in particular, let us say C is a decover of both A and B, and in addition let it be that C is ranked into both A and B, then if you have one processor per element of A, B and C, then you will be able to merge A and B in order of D time. In particular, when I take D as a constant, we will find that two arrays A and B can be merged in constant time when we have a cover of A and B, in particular a constant cover. So in our case, we will see that we have three covers for all the merges that we want to perform. Where do we want to perform merges? When we merge the samples to form the new cache of the parent, we will require covers. But then we shall show that covers are readily available. We shall show that the old cache at a node is a cover for the new samples at the children. In particular, these are three covers. Therefore, the children's samples can be merged into the new cache of the parent using the old cache at the parent as a three cover. Therefore, the merge can be executed in order one time, provided we have enough number of processors for every sample element at the children and every cache element, the old cache element at the parent. If we can show that the total number of cache elements and the sample elements over the active band of vertices, we say that a vertex is active if it is not full yet and is still emitting samples. So if you consider the band of vertices which are still active and we sum up the total sizes of the samples and caches at these nodes, and we find that if that is order n, then we find that with order n processors, we will be able to merge the samples at the children into the caches at the parents in order of one time. That is the crux of the argument that establishes that a stage can be executed in order one time. We shall see more of the details in the next lecture. So that is it from this lecture. Hope to see you in the next.